All right, so let's get started. So welcome everyone to the 86 call with CP Tap. And whoever, a lot of noise going back. Good. Yeah, so today we have Maxim. Let's see if I can pronounce the last name. Maxim Barodska.
Barodska. Yeah.
He's going to give us a talk basically about anomaly detection in raw GNSS data. So a little bit of Maxim. Maxim has been in navigation, navigating the realm of IT entrepreneurship with a particular focus on embedded systems and real-time monitoring with high load capacity. And his journey began with the foundation and development of a project named, how do you pronounce that? Is that Units?
Unitas?
Unitas. Nice.
Unitas.
A low-code platform designed to streamline measurement automation. So, I mean, like, I don't need necessarily to go through the bio. So let's just keep.
Yeah, it's not necessary. It's we're going to talk about GNSS only.
Exactly. We're gonna go in depth. So with no further ado, Maxim, I'll give you the floor.
Okay. Hello everyone, and Ahmad, thank you for the introduction. Can you see the screen? My screen? Yes, with presentation. Okay. So I will try not to be very boring. Let's get started. I would like to start my presentation by describing what methods exist to protect time servers from GNSS spoofing. We will start with complex antenna systems. And here we have two methods called null steering and beamforming. Null steering makes a null antenna pattern to the source of interference. The antenna system typically contains 4 elements. This allows to achieve from 40 to 60 decibels of interference constellation from all directions, and it's good enough for jamming mitigation. But this technology is not very well suited for defense against spoofing, because the power of fake signal can be lower than the system noise level. And in that case, the fake signal would simply be invisible to the system. Beamforming is more complicated and requires a large number of antenna elements. So how it works? Since we can calculate the position of satellite, we can form a narrow beams directed to each satellite. This method is much more advanced and effective, but it's also much more expensive. These two methods have common disadvantages. Firstly, it's expensive and it's subject to export control. Therefore, it's quite difficult to use them on a commercial infrastructure. Second, interference suppression ratio is only 40-60 decibels, which is good enough for jamming mitigation, but definitely not enough to resist powerful spoofing. Well, if spoofing is difficult to mitigate at the radio signal level, we can use a concept I called detect and switch to backup. If you have built a complex antenna system, complex synchronization system, you can set up cross monitoring of grandmasters located in different sites. And I know a lot of companies use this approach because it's pretty simple method that requires little investment. But I see two problems here. First, you will detect an issue when your grandmaster has already been successfully spoofed and part of your synchronization system has already received incorrect data. Second, spoofing can be very powerful. and cover huge regions. As a result, all your grandmasters could be under the same attack. Now let's look at our approach. If you have access to the raw data coming from a GNSS receiver, you can detect a data anomaly caused by spoofing or jamming, and you don't need to search for spoofing signatures, which is hard enough. You just need to recognize that something is not going as usual. And what are the advantages here? You can detect that something is going wrong before it affects your time saver, and it could be a software-only solution, without additional hardware. Disadvantages. You need to get access to the raw GNSS data, but this could easily be done for the open time saver architecture. Before we jump into how to detect anomaly, I would like to explain why we should pay attention to the problem of GNSS spoofing now. The first mentions of spoofing were from Russia 10 years ago. In major Russian cities, anti-drone systems utilizing GNSS spoofing were deployed, and spoofing has become a problem for civilian infrastructure in Russia. But for the rest of the world, the problem was only theoretical. Let's look at what we have now. This is a screenshot from gps-sdr-sim.org website. And this is an analysis of data coming from aircraft tracking system called ADSB. These red dots show locations where aircraft experienced difficulties in receiving GNSS signals. And as you probably realize, all we see here is interference powerful enough to block GNSS signal reception at high altitude. This is even more interesting if we take into account that the aircraft body itself has a good screening feature. So here we see only really powerful interference. This screenshot I took 3 days ago, and we see that all Baltic states are covered by interference. A little bit of interference in the border of Norway and Finland with Russia, here and here. A significant part of Black Sea coastline is covered too. And right now, Israel is using electronic warfare for their defense. And the entire conflict region is covered by interference. What it means for you? If your critical infrastructure is close to these regions, you should definitely think about GNSS interference protection. And next, interesting news. According to some news portals, GNSS spoofing is used on ships to bypass sanctions, for example, to export Russian oil. Here is a link and QR code to a really interesting article from the New York Times. The investigators utilize data from the vessel tracking system and satellite images and identified multiple episodes of deliberate spoofing to cheat the vessel's tracking system. According to the satellite photo, these ships were docked in Russian ports. At the same time, the tracking system showed a completely different location. And here is our data recorded in the north of Norway half years ago. Our system detected several episodes of a very long-term GNSS jamming, and we believe the interference was coming from some vessel at sea. Why we think so? First, this is a very remote location. There is nothing there except the sea and the mountains. No any infrastructure that can potentially generate such powerful and long-term event. Here we see more details here. It's quite possible that someone used GNSS jamming to illegally enter Norwegian territorial water. So that means if your critical infrastructure is located near the coast, you could also be subject to such an unintentional attack. Okay, now why spoofing has become so common or so commonly used, widespread? Because it has become very cheap and simple. Now any person anywhere in the world can buy a software-defined radio, like on the picture, can download one of the GPS signal simulation application from GitHub and run his own GPS spoofer in minutes. On GitHub, we have found about 700 forks of applications for generating IQ data for GPS signal simulation. This confirms, high level of interest in this topic. Okay, of course, if you use only minimal set of equipment like HackerF, and laptop, it's possible to successfully attack only a GPS receiver at a short distance. But if you add power amplifier and directional antenna, it's possible to cover a huge distance. For a successful attack on a multi-constellation GNSS receiver, it's possible to additionally use a GNSS jammer to block another signals. And actually, we see this kind of scenario very often because multi-constellation generator, GNSS generator is still expensive, and it's much easier to spoof GPS only and just block another constellation. And it's just very cheap and effective scenario for anti-drone system, for example. Okay, a few words about types of spoofing attacks. We identify two types of attacks, non-coherent and coherent. During a non-coherent attack, a fake signal is generated with wrong pseudo-ranges, Doppler, PPS phase, and in the first few seconds of the attack, it's necessary to force a target receiver to lose track of real signals and go into search mode. Only after that, the target receiver switches to false signals and starts producing incorrect values. Coherent attack assumes that in the first seconds, the fake signal is identical to the original one in all parameters. The target receiver in this case immediately switches to the fake signals, and then it's possible to implement smooth time or coordinate shift. I suggest you watch a very clear animation about types of spoofing attacks on this link in this QR code. So this screenshot shows an example of a GNSS receiver's response to a non-coherent attack. And by the way, all the data I will show you during this presentation was recorded at JAMA Test 2023 in Norway a month ago. And so this is the real scenario that was recorded by our system. At the top, you can see the spectrum waterfall. And it's easy to identify the spoofing start time here. Below, we see horizontal position accuracy and signal to noise average. So here we see that in the first 15 seconds of the attack, there is a decrease in the signal to noise ratio. Then the receiver switched to fake signals and lost fix. And finally, after about 30 seconds, we see the fake coordinates. This is how a receiver behaves under a non-coherent attack scenario. Here's an example of a coherent attack. Here we can see that the receiver switched to the fake signals immediately after spoofing on. Then for the first 5 minutes, nothing happened according to scenario, but then the coordinates were smoothly shifted. This is a coherent attack scenario. Okay, now let's look at what data is available to search for anomalies. Absolutely all receivers supports the NMEA data protocol, but the protocol contains only basic data that can be used for our purpose. Of course, you can validate timestamp coming from your receiver, but you have to be absolutely sure that your timestamp is correct. Then you can check coordinate accuracy. For a static point, for static position, the velocity must be near zero, obviously. And perhaps the most interesting data here is signal-to-noise ratio for each satellites. So if you are lucky enough, you have an access to binary data protocol, for example, UBX from uBlocks, and there is a much wider set of important data available to you. With gain and RF spectrum, you can estimate the power of RF signal, of RF interference. You can monitor residuals. You can validate pseudo-range and Doppler. And if your receiver supports phase measurement, you can analyze carrier phase. Okay. Let's start with the simplest algorithm, coordinate monitoring. And here we see one non-coherent attack with a sharp coordinate shift, and two coherent attack with a smooth coordinate shift. And we see that for all these attack scenarios, it's very easy to implement the detection algorithms. You just need to calculate the difference between your reference coordinate, your reference position, and coordinates coming from a GNSS module. That's simple, right? The first weakness of this algorithm is that you only detect spoofing when you have been already successfully spoofed. And it's too late, actually. A GNSS receiver may start generating false PPS a few seconds before false coordinates. This means that a time-saver algorithm could have enough time to readjust your local oscillator. Okay, another weakness is obvious in this screenshot. The GNSS generator actually can simulate your coordinates very precisely and manipulate only time. That's exactly the scenario we're seeing here. Here we see that our system detected GPS and Galileo spoofing, while the horizontal position accuracy remains at the same level. And it was a time attack scenario we recorded at JAMA Test 2023. Okay, and if you want to discover how it's possible to move the PPS phase of a target time saver using coherent spoofing, you can watch the video at the link in this QR code. There I demonstrate the different attack scenario on a time saver. Okay, let's go to the second most popular parameter for anomaly detection, signal-to-noise ratio. And here in the picture we see 9 episodes of powerful spoofing. And each time the average value of the signal-to-noise ratio increased significantly. The average value under normal condition was about 30 decibels. Under spoofing, it was about 45 decibel. So to detect such a case, you can simply set the limit, for example, 10 dB above the average level. It's quite easy. Well, here is a different situation. The power of fake signal can be low, and the increase in signal-to-noise ratio is also low, very minor, about 4-5 decibels above average level. Nevertheless, it was enough to shift the coordinates. There is a piece of timeline right here. It means this episode it was a successful spoofing here. And for this case, it's quite difficult to set a limit. I would say not easy, because you have to avoid false positive. Okay, and this is a data for a few days for GPS only. And it became obvious that setting a simple threshold will not give you much. The average value of the signal-to-noise ratio and number of visible satellites fluctuates widely during the day, even without any interference. And of course, it all depends on where the antenna is installed. This particular data is acquired with an antenna that only partially sees the sky. That's why the fluctuation are so strong. Okay, here here's the same actually episode, which we saw on previous slides. And it's good actually idea to monitor the distribution of signal to noise ratio between satellites, for each satellites. On the left, we see a situation before spoofing for this particular timestamp, and on the right, during spoofing here. And we see that before spoofing, most of the satellites had a signal to noise ratio below average. During the spoofing, the distribution changed. So it's just another idea what's to monitor to detect anomaly or spoofing. Okay, and this is an example of two attacks. For the top plot, it's absolutely clear how to detect, and actually any method will work. The bottom plot show a non-coherent attack with low power, and some of the satellites got spoofed. For example, here, and some didn't. And simple methods will not work here. Okay, let's go to the next parameter for analysis, residuals. First of all, what it is? Pseudo-range residuals are defined as the difference between the estimated range to the satellites and measured pseudo-ranges. And in this screenshot, you can see the reaction of a u-blox receiver to a non-coherent attack. I remind you that with a non-coherent attack, pseudo-ranges are very different from the real ones, and therefore the residuals are large. So what we're seeing here, the cursor is put in the middle of the interval where the receiver lost 3D fix here. And on the signal-to-noise ratio graph, we can see that there are a lot of powerful satellites with huge abnormal residuals. And it's a very clear pattern for a non-coherent attack. And please note that residuals monitoring allows you to detect an anomaly before your GNSS receiver starts providing incorrect data. Okay, here on these two plots, we see two cases of a non-coherent attack. On the top, it's a very brutal attack. The residuals grow up to 1 million meters, and it's easily detected. In the bottom plot, we can see that residuals under non-coherent spoofing can only grow to a few hundred meters. And actually, it's hard to set detection threshold, as the same effect can be caused by reflected signals. And if your GNSS antenna is installed in a city with tall buildings, you will definitely have reflections and the similar picture. Also, please do not forget that with a coherent attack, residuals are always about 0. Okay, now let's move on to spectrum monitoring. Some GNSS receivers can report preamplifier gain, spectrum data in some form, and even raw IQ data. And you can use it to detect interference. The screenshot shows data from one of our sensors in which we have implemented this simple algorithm. If a peak power exceeds the set limit, we register an event. Sounds very straightforward. But you should take into account that the power of a fake signal, a spoofing signal, can be very low. For example, in this picture, there are actually 3 spoofing events. In the center, we see a powerful event, and on the sides, there are weak ones that are not even visible on the spectrum waterfall. And actually, in real life, no one generates a spoofing with overpower. Everyone is trying to avoid side effects and impact on neighboring civil infrastructure. So don't expect that you only need to monitor power for spoofing detection, for successful spoofing protection. Okay, if you use GNSS receiver from u-blox, you have access to raw binary data coming from satellites. And here you can find current timestamp, ephemeris, and almanac data. And it's quite possible to implement simple data validation technique, especially if you have access to the internet and you can download a real almanac and ephemeris from NASA website. So actually it's easily enough to monitor only timestamp coming from satellites, for example, time of week for GPS. Here I want to mention a very important topic: a GNSS receiver glitches under and after spoofing. In this screenshot, you can see the data from a u-blox receiver, which did not restore tracking of real satellites after spoofing disabled, until we did a cold reset here. So please keep in mind that different GNSS receivers can behave really unpredictably, not only during spoofing, but even afterwards. Okay, on this slide, you see the complete data set that you can get from a u-blox receiver for anomaly detection. And in general, if you try to detect anomaly in each parameter individually, it will only protect you from the most basic attack scenarios. To achieve much better result, we treat this data as a set of intercorrelated time series. And here you see an example of data correlation. Okay, now a few slides about our spoofing detection system. We have 2 sensors, 2 models, a 3-channel probe with built-in signal analyzer, and a signal channel probe. These sensors send all the measured raw data to the cloud every second. And in the cloud, we have implemented various anomaly detection and classification algorithms. This single channel probe can only detect interference using RF signal power monitoring and detect anomalies in raw GNSS data. But this device cannot distinguish between spoofing and jamming. But please take into account this nice integration feature, GNSS output. You can connect this device in between a time saver and a GNSS antenna. And if there is no anomaly or interference, the GNSS signal passes from input to output. If something is detected, the output is disabled, and it's quite simple and effective way how to protect your time saver against spoofing. Okay, and this is our high-performance probe. It sends to the cloud a huge data set from 3 channels and even some spectrum information. And this data is sufficient to detect and even classify all types of spoofing attacks, even the most advanced. Okay, here you see the result of the correct classification of a sophisticated attack recorded on JAMA test 2023, a month ago. On the left in the middle, there is a chart of spoofing detection for each constellation, spoofing probability. and jamming probability on the right. Here on the top, you can see that we use different colors for different constellations. There is a 5 minutes of jamming at the beginning of the attack, then spoofing of GPS and Galileo in combination with GLONASS jamming. So I consider this as a perfect classification result. And another example of successful anomaly detection caused by low power spoofing. If you look at the signal to noise ratio here, you cannot see anything unusual. All you can see is a minor increase in power in band. Nevertheless, our system successfully detects anomaly, and quite quickly, with just a few seconds latency. And after a minute, it classifies this anomaly as spoofing. So I'm finished. Here you can see my contact data. You can reach me via email or on LinkedIn. And if you check our website, you will find more information about our GNSS interference detection system.
Great. So let's open the floor for questions.
So I noticed that all of the examples on the spectrum analyzer are from L1 channels. I'm assuming that you can monitor more than just L1.
Yes, that's right. However, Ahmad, by the way, can you see me?
Yes.
I stopped sharing the screen.
Yes,
Okay.
yes, we can see you.
Yes, actually, our GP Cloud supports data processing of data coming not just from our probes. We can process data coming from ATK base stations or another GNSS receivers. And right now we support ATCM data protocol, a binary data protocol from Septentrio. And in some months we will implement NMEA data protocol support. And our GP Cloud will be able to detect anomalies for all signals. However, our equipment, our probes support only L1 because we want to leave our system cost effective. Because we are a startup and it's quite difficult to sell hardware right now. And that's why we trying to leave our hardware as low cost as possible. And I believe if you want to implement a successful GNSS interference monitoring system, you need to cover a huge area with quite a good density. Because, for example, if you want to detect a military grade jamming or spoofing, you just need to have only one base stations near border with Russia, and it will be enough. But if you want to deal with, with in-car GNSS jammer with very low power, it's better to have quite a big network of sensors, and that's why the sensors must be low cost, and that's why we support only L1. And moreover, I never saw a case when L2 or L5 bands was jumped and L1 wasn't jumped at the same time. Okay, that's our idea.
So L1 always gets the first hit.
Yeah, that's right.
Great. Any more questions?
Which generation of the U-Blocks chips are you using? Is it the Gen 7, Gen 8?
Actually, it depends. But we use 8th and 10th generation.
So also, is it effective against sideband interference? Because a lot of that, sideband interference is partial, right? So doesn't.
Yeah. And I understand. So if this interference affects a quality of GNSS signal reception quality, of course, we will see a degradation in signal to noise ratio, and our system detect and classify this event like a jamming. But our embedded RF signal analyzer has only 60 megahertz real-time bandwidth. But as for me, it's enough actually.
Yeah, I was only thinking back on some experiences I've had in the past. Thank you.
I do have a question. So your device can detect and stop the jamming signal, but at the same time, when that mechanism is kicking in, you also stop receiving the correct the genuine GNSS signal, correct?
Yes, and you're completely right. In general, our system, it's just a detection system. We cannot mitigate. We do not, we don't develop, for example, sophisticated antenna system with null steering or beamforming, which can, provide some kind of resistance against jamming. Our system can just detect and classify interference. But for example, for time servers, it's enough, because if you detect something, you can switch to backup. You can switch to local oscillator, you can switch to another grandmaster. And it's quite a low-cost approach, because sophisticated antenna system is very expensive. It's much more expensive than regular time server. And moreover, sophisticated antenna system just provides, for example, better result, 60 decibels of interference suppression. But if you want to jam, you can generate any power you want, because power is almost unlimited. And it's simple to add additional 10 decibels on generator side. Yeah. But it's very expensive to add these 10 additional decibels to antenna system, to additional suppression level. It's very expensive.
So now once your protection mechanism kick in, do you continue to monitor the this jamming signal, and then also when things back to normal, do you immediately detect and unjam just put everything back to normal, or how does that work?
Actually, yes. Actually, you described correctly. Our system can detect jamming or spoofing, and then after the spoofer or jammer disabled, our system is able to recover to the original satellites, and usually it takes from 30 seconds to 60 seconds. It depends on scenario. It's a completely ready to use system. It's not necessary to make a cold start after each detected spoofing or jamming incidents. Our system is able to automatically recover to original satellites.
Have you looked at possibly creating a feature where you can actually triangulate the source of the jamming transmitter or spoofer?
Yeah, it's our upcoming feature. In our high performance probe, we use a custom-made RF signal analyzer with FPGA, and we can send raw IQ data, which is precisely aligned with PPS phase. And on our server side, we can implement time difference of arrival method. And if you have several probes installed in region, and all these probes are covered by jamming or spoofing, it will be possible to localize the interference. Time difference of arrival is very, I like this method because it's pretty low cost. It's not needed to have a sophisticated antenna system. It's not needed to calibrate this antenna system. And this method works good with signal with noise modulation with broad spectrum.
Gotcha. Sounds great.
Mhm.
All right. Any other question?
Okay, one last question. So, so I heard that it in order to recover, it may take like 30 seconds, right? So if some bad guy they purposely generate these jamming signal every every 30 seconds, then it always paralyze. They don't have to constantly jamming you. They send one jamming signal for short spurts, like 1 or 2 seconds. When you detect it, your protection mechanism kick in, and then it will be a 30 second before you ever recover. And people can just devise these things that paralyze your device. I mean, not paralyze your device, but the GNSS signal can be always paralyzed, I guess.
I got a question. Actually, I wouldn't say that this is some kind of disadvantage of our system. And actually, we try to combine this kind of events. We have a timeout between event, and actually we see the same behavior in real life every day. Why? Because due to signal propagation condition, the power of signal is fluctuated. And for example, if some kind of jammer installed in a car and car is moving and the power profile, it's fluctuated very widely. And our system combines these events, this number of events in one big event. And but we did this intentionally, and actually I do not see any problem with how it can affect critical infrastructure protection. If someone want to jump, why it's needed to jump 30 seconds, then timeout, then 30 seconds again.
Mark, do you want to ask a question? Mark Wright?
Yeah, I had a question about the cloud service. You mentioned that you aggregate the measurements from the probes there, but are there other advantages of having a cloud service? Maybe also analyzing historical data or processing power? What were the reason to opt for the cloud service?
Okay, about cloud, it's just a marketing, it's just a name. The application is called GP Cloud, but actually it's just a web application or a number of web applications, and we can deploy these applications on different servers. But system is designed to analyze real-time data. Right now we cannot process historical data. Probably in future, probably it's not a huge deal to add supporting, for example, Linux file uploading and post-analysis. But just now we do not see this, request from our customers.
And related to the aggregation, how close the different probes have to be together to make useful analysis of co-located probes?
The probe must be installed in some close area only in case you want to use time different time difference of arrival method to localize interference source. But for detection method matter, you just need to have only one probe installed on near your time server, for example, or protected GNSS receiver.
Okay, thanks a lot.
Any more questions? Like I have a question with regards to DAS, like where you have like this system, like I even have like one here, like the antenna. Does have a GPS antenna, brings things in. Like let's say you have it for a legit purpose, and you still want to also detect. Like I mean, if I have a DAS, I probably will have the spoof detection, like going all over the place, thinking this is a spoof signal. Now, let's say, how can I distinguish between? Well, let's say at this point, if I have something like this, I will shut down the spoof detection, but then I will be now vulnerable to real spoofing if that happens, because let's say this is in a building. I'm talking about infrastructures where you're routing the GNSS signal in a hall from an antenna that you have on top, but you still want to have the spoof detection, let's say, enabled. Like, how does that work?
I believe, if I understand you correctly, you're asking about what if you generate your own fake signals in your lab, and this signal can cover.
It's not necessarily like that. It's like more, you have an infrastructure where you, and I've seen this, not us, but I've seen this, like where you have a DAS system where you're bringing the signal, like the GPS signal down, and then you're radiating.
You mean retranslator?
Yeah. So now that will be considered a spoof, I'm assuming, based on all.
Yes, it's completely, it's definitely must be considered like a spoofing. And this is the major benefit of our system, because we are able to detect even a signal coming from a retranslator. And why it's important, because we saw a lot of cases from our customers who faced with problems caused by high power signal retransmission, not intentional spoofing. And it's needed to be detected and classified as spoofing.
Yeah. Because this opens really, like it's like a double-sided sword. Like for one side, yes, then you want to, let's say, detect or distinguish between this retransmitted signal and not consider that a spoof, and then let's say go for.
It's not possible, Ahmad. It's not possible, because a retransmitted signal, it's a spoofed signal.
That's true. All right.
It's.
Yeah, I mean this, like as I was saying, like then you disable all this spoof detections because because let's say in cases where you need a retransmitted signal, but now you make yourself vulnerable to real spoofing that can happen on the source where it takes a like retransmitter. So it's important to find a way to distinguish this.
Actually, to detect a signal coming from a retranslator, we utilize one special algorithms.
Yeah.
And I believe it's possible to disable, to make some settings and disable this particular algorithm. But in that case, you will be vulnerable to a precisely executed deliberate spoofing attack, coherent attack. But the system still will be able to detect a non-coherent attack.
Yes. Yes. Any more questions? Eric, did that answer your question? Like, because this was more a follow-up of what you asked.
Yeah, I guess so. Thank you.
Any more questions? All right. Hearing none, we'll give you guys back 10 minutes. And thanks again, Maxim, for the presentation. So hopefully Maxim sent me the slides. So we'll put the slides on the wiki with the recorded session, and we'll see you guys in 2 weeks.
Thank you. Bye-bye.
Thanks.
Bye, everyone.
Okay, Ahmad, thank you for the opportunity to give this presentation.
Very welcome. All right. Bye, everyone.
Okay, thank you. Bye-bye.
Thank you, guys.